Now that we've learned how to calculate the equilibrium constant and to write the expression, we are now going to learn how to manipulate equilibrium expressions as well as reactions. In this example, we've got hydrogen gas reacting with iodine gas to form two molecules of hydrogen iodide gas. K1 in this case is 850. Notice we're raising the concentration of hydrogen iodide gas to the power 2 because we've got two molecules of hydrogen iodide gas forming in the balanced reaction. We're going to divide by the reactants multiplied by each other. In this case, our reactants are hydrogen and iodine. And both of these are being raised to the power 1. Sometimes chemists are lazy, and so they don't put that power 1. But we are raising them to the power 1 because we only have one molecule of each reactant in this case. Now this is the reaction reversed. We've got two molecules of hydrogen iodide gas forming one molecule of hydrogen gas and one molecule of iodine gas. K2, which is the new equilibrium constant, is your products times each other, and in both cases we have a coefficient of 1, just like in the reaction above. And then we're also dividing by the reactants. Now our reactant is hydrogen iodide gas, and we're raising it to the power 2. Now I would like you to pause this video and then try and find out what the relationship between K1 and K2 is going to be. You might want to jot this on a piece of paper or pause the video. I'm glad you had an opportunity to try and figure out this relationship. If you weren't able to figure it out, we're going to talk about it. Now notice here, these equilibrium expressions K1 and K2 are very similar. We have just flipped the denominator and the numerator for these two reactions. And so the relationship between K2 and K1 is K2 is equal to 1 over K1. Now if you remember, our K1 is 850, so 1 divided by 850 would give us this number right here. 850 has got two significant figures, so if we round this number to two significant figures, we would get 0.012. Now we're going to see the effect of multiplying the reaction by a coefficient. The coefficient that we're multiplying this reaction by in this case is 2. Notice now we multiplied the reactants by 2 as well as the product, so everything has been multiplied by 2. We're going to generate a new equilibrium constant, K3, and K3 is Hi raised to the power 4 because we've got 4 molecules of hydrogen iodide gas, hydrogen raised to the power 2, iodine raised to the power 2, because we've got 2 molecules of hydrogen gas and 2 molecules of iodine gas. Again, you can pause this video to see the relationship between K1 and K3. You might want to jot this down. Hopefully you were able to figure this one out. If not, no worries. Notice here K3 looks very similar to K1. What we have done to K1 is we've raised K1 to the power 2. Now this number is very familiar. It's the very same number that we used to multiply this whole reaction by. So the relationship between K1 and K3 is if we multiply a reaction by a certain coefficient, then we can raise that reaction by the coefficient we've multiplied by to find the new equilibrium constant. So the new equilibrium constant would be 850 squared, which gives us 722,500. And because we have 2 sig fig in our original equilibrium constant, we're going to end up with 2 sig fig in our final answer. Now we're going to look at the final type of manipulation that we can do. With this manipulation, we're going to be adding different reactions. I think you remember from General Chemistry 1 when you did Hess's law that you could add reactions and generate a new reaction as a result of that. Notice reaction 1 has equilibrium constant K1, reaction 2 K2, and reaction 3 K3. I would like you to pause this video and generate the equilibrium constant expressions for reactions 1 up to 3. Notice we generate these 3 equilibrium constant expressions. Now, this is something that you are probably getting more efficient at doing. Notice it's always your products divided by your reactants, and you're multiplying your reactants. In these cases, you have 2 different reactants, so we have to multiply 2 reactants. And for reaction 1 and reaction 2, all our coefficients are 1, so we have 1 coefficient for the reactants as well as the products. Now if you look at reaction 3, we've got 2 molecules of reactant B, and so we're going to raise it to the power 2. We notice here that there's 2 molecules of reactant B right there. So we raise B to the power 2. I hope you are able to generate these equilibrium constant expressions. Now the final step is for us to see the relationship between K3 and K1 and K2. You may want to pause this video and see if you can establish the relationship between them. So I hope you're able to get the same result. If not, we're going to discuss it. As you can see here, the relationship between K3 and K1 is that K3 is equal to K1 times K2. This is our expression for K1 and this is our expression for K2. Notice that the C's are going to cancel because they're in the denominator and the numerator. And notice that there's a B here and we also have a B here, and so B times B is going to be B squared. So whenever we're adding 2 reactions, the new equilibrium expression is going to be the equilibrium expression of each individual reaction multiplied by each other. So these are the major manipulations that you're going to face. You may need to multiply one reaction by a coefficient or reverse a reaction and then add them up, but you already have the tools to see how you can manipulate your equilibrium expression if you're reversing a reaction. You also have the tools to manipulate your reaction if you're multiplying it by a coefficient. And just to recap, if you are reversing a reaction, you're going to find the inverse of your equilibrium expression, so 1 over your equilibrium expression. If you multiply your reaction by a coefficient, then you're going to raise your equilibrium expression by that coefficient. And then if you're adding reactions, you want to multiply the equilibrium expressions of the reactions you're adding. Thank you, and I look forward to exchanging some more ideas in the next coming slides.